Okay, welcome back to another video. In last video we did Prim's algorithm. In this video we're gonna explain Kruskal's. Okay, Kruskal is very similar to Prim's, but it works a little bit differently. So the way, if you remember in Prim's algorithm, we picked a node. So for example, we picked A, and then we said, all right, let's see what edges are leading out of A. And then we noticed that, we had an edge leading with a weight of 1 going to D, right? And then we had another edge going to B out of, going to B, and that was of weight 1, and then we had another edge out of A going to C. There we go. With weight of, I didn't put the weight on there. Let's go ahead and do that, of weight 2. Okay. So Prim's algorithm would say, all right, pick the cheapest edge, right? So we would have picked one of AB or AD, so maybe we pick this one, right? Now we had A and D, and then now we explore the edges that are coming out of D. So we would have found this edge for 4. We would have found E, node E for 2. We would have, I think that's about it. Right, so now we explore the cheapest edge, and the cheapest edge would be going to be. And now from here, so far we have done this weight here, and we have done this weight, right? And now we go ahead and I'm going to try this again. So from B we have discovered a new edge of 3, and we have discovered a new edge to E, which is of 2, right? And we should highlight B probably because it's in our discovered list, right? And now we pick the next cheapest edge. So in this case, I don't know, maybe we'll pick B to E, right? And now E will give us E actually, yeah, will just give us one new. I forgot to explore the edges from D, right? D is in our list here. So before I go on to include E, I have to make sure I show all of the edges coming out of D. So D goes to F. Here we go. Let's do that with a different color. Goes to F. And then we have, so that's of cost 2. And then we have D going to G. There we go. And that's of weight 1, right? So now we pick the smallest cost. So the smallest cost in this case will be D to G. Now G is going to be in our list, and then we keep on, doing this. Now the edges that are coming out of G. So if you guys notice how Prim works is Prim's algorithm, right? It picks a vertex and explores all explores all edges and picks the cheapest one. Right, and we do that we repeat this where we explore all edges and pick the cheapest vertex. We do that for all of explored vertices. So we have a list that grows, or a set that grows, and we keep doing this highlighted portion here over and over again. And this is how we add, nodes and edges to our explored list. So that's how Prim's works. It starts with a vertex, okay, and then adds the edges. Now, Kruskal kind of does the opposite. It picks an edge first. So Kruskals will pick the cheapest edge, add it to the tree, given that making sure that we don't introduce a cycle. Okay, so again, let me say it again. Prims picks a vertex and explores all edges. Cruise call doesn't explore the vertices, doesn't pick a vertex, it picks the cheapest edge. So it builds the tree by picking edges. Okay, I'll say that once again. It picks the cheapest edge, tries to create a tree out of it, and making sure that we don't introduce a cycle by picking an edge. So what do I mean by that? Well, let me go ahead and erase, we can actually leave that there. So I'm gonna go ahead and write the graph without the edges. So I have A, and then we have B, and then C, and then D, and E. Okay, and let's see F and G. F, and then we have G. Okay, no edges in there. Then we need to find the cheapest edge. So we list all the edges, in sorted order. So we'll say here, list of edges in sorted order. So let's see what we got here. We have AD, or let's say AB at a cost of 1. We have AD at a cost of 1. We have DG at a cost of 1. And then we have AC at a cost of 2. We have BE at a cost of 2. We have CE at a cost of 2. We have DE at a cost of 2. And then let's see, we have DF at a cost of 2. We have FG at a cost of 2. We covered DE, we covered CE, we covered BE. All right, then we have CB at a cost of 3. And then I have CF at a cost of, CD, I have CD at a cost of 4. And then we have, let's see here, DE at a cost of 5. I think I got them all. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so now we, the idea is that I pick the cheapest edge, so AB, right, it's 1. I go ahead and make AB in here. And is there a cycle? There is no cycle. Then I go and say, what's the next cheapest one? Is AD. Is there a cycle? No, there is no cycle. There we go. Then it's DG. Let's go ahead and build DG. There we go. There is no cycle. We're fine with this. Then we go AC. There's no cycle, so we're going to put it there. Then we have BE. There's no cycle. We put it in. So we did AC, we did BE. Let's see, CE. All right, so CE there introduces a cycle, so we're not gonna put it in the spanning tree. Okay, so we're gonna say no to CE. DE introduces a cycle. DE is right there, there is a cycle, so we're gonna skip DE. DF is good, so we're gonna put DF in here. Right, there is no cycle. I'm gonna say yes to DF. Then we have FG. FG let's see, there introduces a cycle, so we're gonna say no to FG. CB introduces a cycle right there, so we're gonna say no to CB. There we go. CD. Where's CD? CD introduces a cycle, so we're gonna say no to CD. And then DE introduces a cycle right there. So we're going to say no to DE no, that's not D, that should be CF, the last one, because you already did. This should be CF. Let's go ahead and fix that quickly, but it doesn't matter because we're going to say no to CF. All right, so that's how it works. All right, so one way of implementing this, right, the naive way maybe I could say, or the one I explained right now, add an edge and then make sure that the edge doesn't make a cycle. Now, and then to add an edge if it doesn't make a cycle. So every time, let's see, if it doesn't make a cycle. So every time I add an edge, right there, I have to run some sort of an algorithm that says it doesn't have a cycle. So this edge doesn't make a cycle. And if you guys remember, we did how to find a cycle. We just run BFS traversal on the graph, and we can find if there's a cycle with BFS. So that's one way of doing it. Another way of doing it is to use what is called a union find data structure. Okay, and you haven't seen this before. This is a union find data structure. Okay, so let's see how to do that. Let me go ahead and quickly, actually let's erase the graph that we had here, and I'll show you how the union find data structure works. Okay, and let's see if there's an easy way to kind of unhighlight all of these. And we can go ahead and just write them over for our example. Okay, so let's go ahead and write them quickly. I have AB at a weight of 1. I have AD at a weight of 1. I have DG at a weight of 1. And then we have AC at a weight of 1, at a weight of 2. I have BE at a weight of 2. I have CE at a weight of 2, and I have CF at a weight of 2, and then we have DF at a weight of 2, and I have FG at a weight of 2. I think we covered all of them, and then we have BC at a weight of 3, and we have CF weight of 5. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, I missed one. Let's see. AB, AD, DG, AC, ACBE, CE, CE. Then we have CF, DF, FG, BC3. Oh, I forgot CD. We have a CD of 4. CD of 4 and CF of 5. There we go. CD of 4 and then CF of 5. So the idea in the union find is just kind of detect cycles in a smarter way. Oops. Or should I say more efficient or smarter way. So let me show you how this works. We're gonna treat like each vertex being in its own set, or each vertex being in its own like island. Okay, so it kind of looks it's kind of like something like, okay, A is its own little island, B is its own little island or set. You know, all of these vertices are in their own sets or islands. Okay, like this. All right, and then let's go ahead and write that. So we'll say up here, we'll say vertex. So we have the vertices A, Let's make some more room here. A, B, C, D, E, F, and G. Let's write that a little more straight. We have A, B, C, D, E, F, and G. Okay, and then we'll say what set do these belong to? So on the bottom I'll say set. So A belongs to the set that we'll call it the A set, B belongs into the B set, C belongs into the C set, D belongs into the D set, E belongs into the E set, F belongs into the F set, and G belongs into the G set. So I'm just calling the sets the same as the vertex, okay? And then we'll have like a picture, a representation of what is going on here. So A belongs, pick another, sure, we'll do this. A belongs in its own set, B belongs in its own set, C belongs into its own set, D belongs into its own set, E, everything is the same, F, and G. Okay, so now you can kind of guess what's going to happen. I'm going to look at the first edge here. I'm going to look at AB. All right, and then I'm going to say, all right, let's go ahead and make the connection as long as they're in different sets. So as long as A and B are in different sets, then I can make the edge. If A and B are in the same set, right, then there will be a cycle. So I'm going to go ahead and make the edge between, let's use a different color here, between A and B. Okay? So now we have to decide whether to add A in B set or whether to add B in A set. Okay? So I'm going to go ahead. It's up to you really how you want to do this. It doesn't matter. So whether to add A in B or B in A set. So I'm going to take B and I'm going to add, I'm going to take A and I'm going to add it to B set. So I'm going to go ahead and you guess what I have to do? Can you guys guess, right? I'm going to change the A set here to say, and we'll use a different color, to say B. Okay, so A, the vertex A now belongs to B set. So instead of now here for A being in its own set, now A is going to go into B set. So I can kind of come here and change the picture, right? And now it's going to be A belongs to B's set, right? All right, so let's move to the other one. Now I have AD. I'm on to the next edge here, AD. All right, let's see. A is in B set. You guys see that? A is in B set. And then C is, oh, I'm sorry, we're doing DG. Whoops, we're doing DG. Backtrack. No, we're doing AD. AD. I was right. We're doing, my brain just move on to the next edge. We're doing AD. Okay, so A is in B set right there. And then we have D. D is in D set. So in different sets, right? So I can go ahead and again, I can add D to A set or I can add A to D set, but A is already in B set. So let's go ahead and add D to A set. So I'm going to say, all right, I'm going to add a D to A's set right there. So now we're going to take D here and I'm going to say, hey, A is now in, where did my pen go? We'll say D is now part of A's set, right? And I already made this, made a notion of that right there. Okay, I've recorded that. So now D is part of A set, A is part of B set. So essentially D is part of B set. Okay, so I'm gonna go ahead and include now D into the set here. Okay, let's go ahead and add the edge. Let's not forget to do that. All right, now we have the next one. The next one is DG, right there. Let's go ahead and erase this one. So we are in the G. Okay, now let's see here. D, where is the highlighter? D is, let's see, D is in A set, and A is in B set, and B is in B set. So D is in B set. I could have also followed my drawing here. A is in, D is in A's, and A is in B set. So that's, oops. So D is in B set, and then G is in G set. Okay, so in different sets. So I can go ahead and add D here to our set. There we go. So I can go ahead and make the edge here D to G. Okay. All right, so I'm going to add G to Ace to D set. So raise this here, and then I'll say D here. Okay, there we go. So we're going to take the G from here. Oops. There we go. The G from here, and we're going to add it. We set two D's. Let's take a different color here. G's to D. Know that I can follow the link, and I can just make it G be part of B. It's up to you. I'll just do it this now for maybe. I'm not paying the price now to traverse. I'll pay it later. Okay, so let's see the next. The next one is AC. All right, so we are here now. Okay. Let's go ahead and see let's follow the drawing here. A is in B set, and C is in C set. Okay, so I can go ahead and include C like that. Let's go ahead and include the edge right there. Right, and now I can go ahead and say, okay, C is in Ace set, so I'm going to take get rid of the C, and we'll say C is a different color. C is here. Okay, so we're going to modify this to say, oops, say A. Okay. I hope everybody is still following. Next we have BE. All right, so let's take a look. B is its own set, right there. B is its own set, and E is its own set. So I can just make the set of E to be the set of B right there. Okay, so we're going to go ahead and add B to the E to the set of E, right? So we're going to do this there. Okay, we'll do that. Okay, let's highlight B and E here. Okay, and then I have C and E. Now you'll notice that CE here, they're both in the same set. So let's see how we actually came to that conclusion. Well, let's see. C is in A set, and A is in B set, and B is in B set. So C belongs to the set of B, and then if I look at E, E also belongs to the set of B, right? So they both belong to the same set. So we'll say no to CE. So I have to traverse the path. You have to follow the path to figure out what's in the same set. And I keep going like that, right? Next I have CF. So let's see. C is in A set, which is in B set, and then F is in F set, so I'm going to go ahead and add F to C set, which is A. Okay, and then we're going to go ahead and add a C and F. There we go. That's the edge that we want. We'll say C and F. I didn't draw that on there. That should be on there, and that has a weight of 2. Okay, we didn't. I forgot to put it on the graph. Maybe that's why I was getting one less edge. There we go. All right. Anyway, now we have C and F here. Okay. Let's highlight it and add it to the. There we go. And then we have D and F. So let's follow. D is in A. So there we go right there. D is in A and A is in B. So D is in B. And then I have F. F is in A, which A is in B. So F and C are both in the same set. Actually, I could have seen this right from here. I'm sorry, C and F. C and F, right? So we don't want this one here. And we keep, technically, we already have the spanning tree, so we'll end up disregarding all of these. Okay, so this is the union find data structure. It's a data structure for sets and combining sets and finding things in sets. And as I said, you'll probably see this later on. Later on when you take CS, I think 300 algorithms and data structure. Okay, I hope this made sense. Let me know if you have any questions.